Welcome to the problem solving session of heat and temperature. Today we have 10 questions about measuring heat, temperature compressions. Finally, we will look at the heat exchange of different objects with different temperatures. So let's start with the first question. We have a bowl of water at 20 degrees Celsius and we will find its Fahrenheit equivalence. This is our general relation between Celsius, Fahrenheit and Kelvin. I will use the left side of the equation and the Celsius was given as 20 degree. So from here that when I cross multiply 20 divided by 100, that's equal to F minus 32 divided by 180. So from the cross multiply, I will have 3,600. That's equal to 100F minus 3,200. And from here I can find, if I send this one to the other side, I will have 6,800. That's equal to 100F. And from here I can find F as 68. In this one we have some liquid at 80 degree of Celsius and we will find its Kelvin equivalent. By using this relation, this one is 80 divided by 100, K minus 273 divided by again 100, cross multiply, I will have 8,000 equal to 100K minus 27,300. And if I send this one to the other side, I will have 35,300. That's equal to 100K. And from here I can find K as 353. We will find again the Kelvin scale, but this time I have Fahrenheit, which is 97 degree. And I will use the right side of the relation. And again from the cross multiply, 97 minus 32 divided by 180, which is equal to K minus 273 divided by again 100, cross multiply, I will have 65 times 100, that's equal to 180K minus 180 times minus 273, which is equal to 49,140. And from here I can find K as 309. In the fourth one, we will find the Celsius and Fahrenheit equivalence. I have 383 degree Kelvin temperature here. From the usual equation, I find the Celsius scale of this temperature as 110. So let's find it. If I use the relation again, C is equal to F minus 32 divided by 180. And 100. By using this relation, and I'm trying to find the Celsius, so the K was 383 Kelvin. So from the cross multiply, I will find C as 110 degree of Celsius. So how about the Fahrenheit? This time I will use the right side of the relation, 180, which is equal to K minus 273 divided by 100. And the K was again 383. From here I can find the Fahrenheit as 230 degree. Let's continue with a question about heat capacity. It says, how much energy is needed to heat 100 grams of water from 10 Celsius to 30 Celsius? And this is our formula. Q is equal to mc delta T. We try to find the Q, which is heat. When we put the given values, we will have Q is equal to 100 times 1 times delta T, which is T final minus T initial. So from here I can get 100 T final 30 degree minus 10 degree. That will be equal to 100 times 20, and that's equal to 2000 calories. Again, we have a similar question, so let's find out the needed energy in terms of joules. The specific heat capacity for aluminium in terms of joules is 900. When I put the values in their places, I will get 0.2 times 900 times delta T, which is 70 minus 50. And that because it's in kilograms, we need to transform the gram to kilogram. So from here I can get 3600 joules. This one is also very similar. Again, by using the same formula we can get the answer. That because specific heat capacity of copper is 386, and that because it's in kilograms, as you can see, we need to transform the gram to kilogram. This gram into kilogram. I will find the needed energy as 0.5 in 100 times 386 times delta T, which is 10 degree. So from here I can find as 193 joules. Okay, this time we are looking for the temperature increase. If we add 54 joules to 10 gram of aluminium, again we are using the same formula, Q is equal to mc delta T. Again 54 is equal to 10 times 0.9 times delta T, which is I'm trying to find. So from here I can get delta T as 54 divided by 9, and that's equal to 6. In the ninth question, there are 2 cups of waters in different masses and temperatures. We will find the final temperature of them when we mix them. We will equalize them to each other with a basic logic. But first of all, we need to make them in order regarding of their temperatures. And it must be like in this order. T hot greater than T mix, and that's greater than T cold. M1 times C times delta T1, that's equal to M2 times C times delta T2. That because they are same elements, they have the same specific heat capacity, so I can cancel out C. M1 is equal to 800 times T hot minus T mix, because the first one is hotter than the second one, and that's equal to 2 liter, which is equal to 2000 grams times delta T2, and that's equal to T mix minus T cold. I can also cancel out these 2 zeros from here and here, so I will have 8 times T hot was 30 degree minus T mix. That's equal to 20 times T mix minus 24 degree of Celsius. So from here I can have 8 times 30, which is 240, minus 8 T mix, and that's equal to 20 T mix minus 480. So from here I can have 720, which is equal to 28 T mix, and T mix is equal to 25.7 degree of Celsius. Okay, this time we have different elements. Basically, we will use a similar method to solve this. Again, T hot is greater than T mix, and that's greater than T cold. M1 times C1 times delta T1 is equal to M2 times C2 times delta T2. And M1 is equal to 500 times C1 is equal to, let's say, 0.1, just 0.1, times T hot minus T mix, and that's equal to M2, which is 1 liter, and that means 1000 times C2 is equal to 1 times T mix minus T cold. So from here I will have 50 times T hot is equal to 120 degree minus T mix, and that's equal to 1000. That because T cold is 0, I can write 1000 times T mix. So from here I can have 6000 minus 50 T mix, and that's equal to 1000 T mix. T mix is equal to 6000 divided by 1050, and that's equal to 5.71 degree of Celsius. Okay, that's enough for today. Thank you for joining me. I hope you liked the video. Until the next video, see ya.